where you are right now without even moving, you will see an object made of iron. Like if so many other metals, iron is a very, very useful substance, and even other metals. So it is very important that we learn how these metals are obtained. Most of the metals exist in compounds which are found in the Earth's crust. For example, the metal called iron exists in form of iron, oxides of iron, sulfides of iron, carbonates of iron, carbonate of iron. Then we have a metal like sodium, exists in form of rock salt. Rock salt is sodium chloride. We have sodium carbonate, they contain sodium. So from this metal you can obtain, from these compounds you can obtain a metal called sodium. Whereas for iron, you can use iron free oxide, tri-iron tetraoxide contains iron. You can talk about iron to carbonate, which is called the siderite or spathic iron. You can have iron pyrite contains iron. So you can use any of these to obtain iron, and you can use any of these to obtain sodium. These substances from which the metals are extracted are called ores or an ore, and they occur naturally in the Earth's crust. So it's very important for us to know that most metals exist in form of compounds in the Earth's crust, and these compounds are what we call ores. The definition of an ore, which we already have, an ore is simply a naturally occurring substance from which a metal can be extracted. So all these are ores. You can pick any of these and use it to extract the metal of interest. We also have metals which exist in their element form. Those are the least reactive metals, like gold. If you are to extract gold, you just dig. After knowing where it is, you dig and find it there in its element form. The same applies to silver, mercury. Those are the least reactive metals, and for them it's possible to find it in the Earth's crust when it is in its element form. What are the methods that are used to extract metals? The method which we use to extract a metal depends on the position of that metal in the reactivity series or electrochemical series. So we are going to have the series listed here, starting with potassium, the most reactive metal. Then we have sodium, we have calcium, we have magnesium, we have aluminium, we have zinc, we have iron, we have tin, we have lead, we have copper, we have mercury, we have silver, and then gold. Our first category consists of the highly reactive metals. Highly reactive metals. These are extracted by electrolysis of a salt, of a compound, of a salt or a compound e.g. here sodium is extracted by electrolysis of fused same as molten sodium chloride. Then we have another category of metals. These are the moderately reactive metals. The moderately reactive metals, these are extracted by reduction of their ores. I've already mentioned that an ore is simply a naturally occurring substance from which a metal can be extracted. So by reduction of their ores, e.g. Iron is extracted by reduction of iron 3 oxide or tri-iron tetraoxide then these ones are in the category of the least reactive metals. These are extracted. These are obtained by digging the element out of the earth's crust. Simply because these are not reactive, so we can find them in their uncombined form, and therefore they can be existing in their pure form. You just dig the spot where the metal is, and then you dig, you find it there in its elemental form. In our syllabus of O-level chemistry, we put emphasis on two metals, that is sodium and the iron. We put our emphasis there, and we learn about how these metals are extracted. So we are going to begin with the extraction of sodium. Extraction of sodium. Sodium is extracted, as we have just said, by electrolysis of fused sodium chloride. Sodium chloride can be found in the form of rock salt, that is sodium chloride, and even in seawater. Seawater is salty, and the salt which is responsible for the saltness of seawater is sodium chloride. This sodium chloride consists of sodium as one of the elements, that make up sodium. Sodium is extracted by electrolysis of fused sodium chloride to which calcium chloride has been added. Calcium chloride is added to sodium chloride during melting, because the mixture of sodium chloride, sodium chloride alone melts at around 800 degrees Celsius, while a mixture of sodium chloride and calcium chloride melts at around 600 degrees Celsius. So maintaining a lower temperature of 600 degrees Celsius is cheaper than maintaining a higher temperature of 800 degrees Celsius. So lowering of the melting point is necessary to make the process cheaper, and this is done by adding calcium chloride, because the mixture of sodium chloride and calcium chloride melts at a lower temperature, which is easier to maintain and is cheaper to maintain. Thus, by adding calcium chloride, you save some electrical energy and you can make the process occur more cheaply. The process in which sodium is extracted is called the Downies process, because it was invented by a scientist called Downies process. And the cell or the diagram or the setup of apparatus, the setup of apparatus used in this extraction of sodium is called the Downies cell. It is actually an electrolytic cell. In this cell, as we shall see, electrolysis takes place, in which case the electrolyte is a molten mixture of sodium chloride and the calcium chloride. So it is an electrolytic cell, and as we shall see, sodium metal is obtained at the cathode, where it is produced during electrolysis. Now I want us to look at the Downies cell, the drawing of the Downies cell, which is very important, and then we see how it works. So a process is Downies process, and then the setup of apparatus is called the Downies cell. So we are going to look at the Downies cell. The Downies cell. So, a mixture of molten calcium chloride fused or molten sodium, fused or molten sodium. Put it here. Is brought in the down cell using this opening, and once it's poured inside here, it will accumulate inside. So all this is molten or fused calcium and sodium, or it's a mixture. Now this is anode. Sorry. A cathode made of iron. Then we have an anode. An anode made of graphite. Now this cathode here is circular or cylindrical. It rotates. This part here goes around and it comes here like this. So it is in form of a cylinder. This is connected to this, and so the supply of electricity is made at one point, and then here this is the anode, which is the positive electrode. This is the negative electrode, which is the cathode, made of iron, and the anode is made of graphite. Now, during electrolysis, the sodium ions move to the cathode, where they gain electrons and become reduced to sodium metal. When sodium metal is formed, it collects inside this cylinder. Even here, this is where sodium, after being formed at this cathode is formed. This cylinder is circular, and this connects to this around. So when sodium is formed, it moves and it is collected here. This is sodium metal collected, sodium. On the other hand, we have chloride ions. Remember, sodium chloride consists of sodium ions and chloride ions. The sodium ions, we have said, move to the cathode and they get discharged, and then the chloride ions move to the anode, where they lose electrons and become oxidized to chlorine gas. So bubbles of chlorine gas are formed, and the chlorine gas goes away. Chlorine gas is formed as a byproduct, because our interest mainly here is in obtaining sodium. However, when chlorine gas is obtained, it is also kept, because it can also be used for other purposes. So what goes out from here is chlorine gas. So all this is a molten or fused mixture of sodium chloride and the calcium chloride. Now these inverted cylinders help us to trap sodium so that it can be collected in the storage tank. We also have iron gauzes or steel gauzes, or iron gauze. These ones help to separate the sodium metal from chlorine, because if these two mix, remember this reaction is taking the process is occurring at high temperature around 600 degrees Celsius, which is the melting point of the mixture of sodium chloride and calcium chloride. So if at this temperature chlorine gets a chance of mixing with sodium, the two will react and you form sodium chloride again. So the purpose of the experiment will be nullified. So that's why we have this separation, and it is also emphasized when iron gauzes are included in our setup. The cathode is ring shaped, it goes around. So this sodium here is connected to the sodium here, and once the sodium starts to form, its buoyancy pushes it upwards, and it will move and be collected in the storage tank. So that's the process of obtaining sodium metal from a molten mixture of sodium chloride and the calcium chloride. Basically, we have the reactions which take place at the different electrodes. We have said that at the cathode, sodium ions in liquid form, because this is a molten substance, acquire electrons to form sodium metal, again which is in molten form. So this is molten sodium. Remember, the melting point of sodium is even lower than 100 degrees Celsius. So at this high temperature of 600 degrees Celsius, the sodium which is produced is in the molten form. So that's why in our equation we have sodium having a state symbol of liquid. Then at the anode, the chloride ions are also in molten form, and therefore the state symbol should also be liquid, turned into chlorine gas after losing the electrons. So we form sodium here around the cathode, which is made of steel. This is iron and cathode. So the sodium is collected using iron cathode, because sodium cannot react with iron. So the two can be put together without reacting. Then this sodium, after being obtained here, it goes and can be collected under nitrogen. Nitrogen is a substance which has a very low reactivity, so sodium metal cannot react with nitrogen. But if you just expose sodium to air, sodium at that high temperature will always burn in air to form sodium oxide. So the sodium which is obtained may be contaminated with oxides of sodium. So sodium must be collected under nitrogen, as it is indicated in our notes. Why? Because nitrogen is an inert gas. It has a low reactivity and it cannot react with the sodium metal. But if you expose sodium to air, like to oxygen, sodium will always combine with the oxygen to form oxides of sodium, such as sodium oxide or sodium peroxide or even sodium superoxide. So that's why sodium has to be collected over nitrogen. Then chlorine gas is separated from, they can ask you to explain what's the purpose of the so this is supposed to be here. What's the purpose of the steel gauze and this iron cylinder, which is inverted over where sodium is collected from? The issue here is that we are trying to separate chlorine from sodium, because if you expose the two to each other, they will react to form sodium chloride. So that is how sodium is obtained in the down, and that's how the down cell works, and that's how the down process is described. To form iron oxide and the carbon dioxide gas. So here we have, this is sulfur dioxide gas. I put it to here. Put here. This will become 8. And this will become 2. Here we have to do with. So that's how we balance the equation. So if it is siderite or pyrite, please never feed them directly into the blast furnace. They have to first be converted to iron oxide, because the blast furnace understands only two substances, that is iron oxide and the tri-iron tetraoxide. These are the only substances which have to be fed, either of the two, either this or this, that are fed directly into the blast furnace. But we don't feed iron to carbonate or iron disulfide in the blast furnace. We feed iron oxide or tri-iron tetraoxide in the blast furnace. I repeat, we only feed iron oxide or iron tri-iron tetraoxide in the blast furnace, and never do we feed iron to carbonate or iron disulfide. When we meet again, we shall discuss how you can obtain iron from either iron oxide or tri-iron tetraoxide using the blast furnace. I must repeat this so many times, that in the blast furnace, if you are to use the blast furnace, it is iron oxide or tri-iron tetraoxide that can be fed directly into the blast furnace using other substances, as we shall discuss in our next lesson, but not iron to carbonate or iron disulfide. We shall stop here for this lesson, and when we meet again, we shall be discussing about how to obtain iron from either iron oxide or tri-iron tetraoxide using the blast furnace. I wish you the best whatever you are doing. Thank you very much for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.